In this section, we deal with a problem of a plate. This plate have a circular hole located inside inside the plate. See, this is the problem we want to deal with. Actually, the hole is not that big. It is a small hole, but at this stage, we just emphasize that it has a hole, so we draw it very big. In order to deal with this problem, I want to tell you that we should consider this simpler problem. It is more easy problem. Okay, see, this problem is not one-dimensional. Even though it is subjected to the tensile stress in the x direction, you cannot say that it is a one-dimensional problem, because around the circular hole, the stress will be varied, will be changed according to the theta, theta value. At different theta value and also at different radius, the stress around the circular hole will not be the same. So this problem is not a one-dimensional problem, so we cannot use the knowledge of mechanical material in the undergraduate level to solve this problem. This problem must be solved by using the technique of differential equation. Now, before we solve this problem directly, we consider a simple problem like this. This problem is different from this problem. This problem is a solid plate. There is no hole in the middle of the plate. No hole. This plate is a solid plate. And the solid plate is subjected to the simple tension on its two ends. So the simple tension is just this simple tension is just equal to this simple tension. So the boundary condition at the two ends are equals. And also more important, for this solid plate, the stress state is easy to determine, because it is a simple tensile stress state. So inside the plate, according to equilibrium, every material point will have the same stress distribution. And also the distribution is easy. Sigma xx equals sigma 0, because here on the boundary, the sigma xx equals sigma 0. So inside the plate, sigma xx equal to x02. Also, sigma yy and sigma xy are zeros. So for this solid plate with simple tension, the stress states are easy to determine. Now, we want to use such kind of knowledge to help us to determine a part of the stress state in this plate. Now, here we cut a free body like here, like this, a circular free body. Cut it out. In the middle of the plate, we cut out a free body. Take it here, and after the free body has been taken off, then the internal stress is drawn explicitly here. There is some internal stress here, and this is the free body. Now, the stress states along this free body is just the simple tensile stress states, and also this is the simple tensile stress state. So sigma xx equals sigma 0 here, sigma xx equals sigma 0 here. Now we want to say that the resultant force of this distribution of stress equals 0, because see here, we first draw a plate like here. we draw this plate to here. This plate is equal to this plate, okay? See, the stress here is pulling to the right side. Here the stress pulling to the, the stress here pulling to the left side. Now this one pulling to the right side, so they balance to each other. So it is easy to see that along the circular hole here, the resultant force is 0. Okay? Even though the stress along the circular hole is not 0, the stress distribution is not 0, but the resultant force is 0. Okay? Now we consider the plate we considered before. This is the plate with a circular hole in the middle, right? There's low stress, low traction applied on the boundary. Okay, so since low traction are applied on this boundary, so the resultant is 0 here. Now, this plate with some internal tensile stress also have 0 resultant force. So the resultant force of this problem is equal to the resultant force of this problem. They are all equal 0. So according to the Singh-Walan principle, because the resultant force here is 0, the resultant force here is 0. So the stress state away from these boundaries will be the same. So the stress state here away from the boundary, the stress state here will equal to the stress state here. Okay, this is the Singh-Walan principle we had talked about before. Okay, so by using such kind of argument, the stress states away from the circular hole can be determined. It's just like this simple state. This simple state is equal to this simple state, and this simple state is equal to this simple state. Okay, so by such kind of reasoning, the stress state of this plate can be determined partially. Okay, in a part of the plate away from the circular hole, the stress state is easy. We know that they are equal this set of stress component, simple tensile stress. Okay, let us do a summary here. We have a plate with a hole. Okay, so by comparing this plate with this plate, we know that away from the little hole, the stress states can be obtained. It's just in a simple tensile situation. Okay, this plate is the plate we obtained from the solid plate. Okay, by cutting the free body. Okay, so we have already talked about such kind of reasoning before. I just want to write a more complete picture for you. Okay, so now we draw the hole smaller. Okay, here we have a big hole, but they are the same. Okay, this small hole is just the big hole we talk about. Okay, usually how big is the hole? Usually we say that such kind of problem will have small holes. Why? Because when we consider the steel member, okay, when you want to connect some two steel members, you drew a hole, you drew a bore hole, okay, in order to some screw to connect the steel member. But by drawing a hole here for the connection, you may weakening the strength of this plate. Okay, so we want to compute the stress around this little hole. Okay, because there may be some stress concentration happen around this little hole. So how big is the hole? It is just a little bore hole in a steel member. Okay, so we are dealing with a small hole here. The radius small a is much smaller than the thickness of this plate. Okay, not the thickness, the width of this small plate. The width, not the width. The width, okay, of this small plate. The width of this small plate is 2b. Okay, so b is much bigger than small a. Now we want to decompose this problem into two problems once again. So see, this is another decomposition. Okay, this decomposition take this plate into this one and this one. This is a circular plate with a small hole. Such kind of decomposition is different from this one. This one is a solid plate, okay, we talked about before. This is a solid plate. We cut the free body, okay, to make it as a plate with a hole and a free body. But now we want to decompose this plate again. So this is another kind of decomposition, okay. We want to decompose this plate into two part two, okay. So this is not a solid plate. So such kind of decomposition is different. Okay, we want to decompose this plate with a circular hole into two parts. With this part and this part, this is a free body. Okay, we draw a circular region here and take it out. Okay, as a free body. And also because the stress stay here is simple stress. Okay, simple tension. We had mentioned before, simple tension here. Okay, simple tension here. Okay, so away from the little hole, the stress stay is in simple tension. So away from the little hole, the stress stay here is simple tension. So along this circular boundary, the stress stay is in simple tension too, because this circular boundary is far away from the little hole. Okay, so this is what we have here. On this circular boundary here, the stress stay is in simple tension. Okay, understand what I'm doing now? So simple tension here, and also on this circular boundary, the stress stay is also in simple tension. Okay, do you understand? Now, okay. So this plate can be decomposed into this plate and this plate. But actually, the stress stay in this plate have been obtained because this stress, the material here is just the same as the material here. So the stress stay here is just like this. So the stress stay of this plate with a big hole have been obtained. Okay, so we don't worry about the stress stay here because this plate with a big hole have the same stress stay with this one. Okay, now so we focus on this part. This is a circular plate with a circular hole, small circular hole. We don't know the stress stay inside this circular plate yet. Okay, we will compute it later. And once we obtain the stress stay here, if we have done this, then the stress stay of this whole plate is obtained. Okay, because outside the circular region, the stress stay is this, and inside this circular region, we have solved this problem. And okay, so the stress stay of this plate can be determined totally if the circular region can be solved. Okay, so the rest of this class focus on the stress stay of this circular hole with a small circular this circular plate with a circular hole. Okay, Now we take it here. This is the focus of the rest of this class. Okay, we take it here. This is a circular plate with a small circular hole. Okay, and the circular hole is stress-free, low traction applied along this small hole. And on the outer boundary of this circular plate, the stress state is in simple tensile stress state, right? Low sigma YY, low shear stress. Only sigma XX equals sigma 0. Now, we want to argue that such kind of simple boundary conditions can be decomposed into two sets of particular boundary conditions. The first one and the second one. This means that we want to decompose this problem again into two problems. Okay, we have a lot of decomposition. We first decompose this one to this one and this one, and then now we take this one here and then we decompose this one into two problems again. Okay. In the problem 1, we have the periodical boundary conditions like this: sigma r equal to sigma 0 over 2 times cosine 2 theta, and sigma r theta is minus sigma 0 over 2 times sine 2 theta. So we have a periodical stress distribution on this circular plate. Okay, this is the first problem. The second problem, we have some simple visually symmetric simple tensile stress state along a circular plate. Okay, the visual stress here is sigma r equal sigma 0 over 2. Okay, why such kind of simple tensile stress states can be decomposed into this periodical one and this visually symmetric one? I will explain it later. Okay, right away. Here, we talk about the decomposition of the boundary traction, sigma xx equals sigma 0 here. Just, no. Okay, and let me, sorry. Yes, here, sigma xx equals sigma 0, and sigma yy here equals 0, and sigma xy here equals 0. With such kind of stress state along this boundary, okay, what happened to the if we express it in terms of the polar coordinate? Remember, sigma xx equals sigma 0, sigma yy equals 0, sigma xy equals 0. Okay. Here, according to the formula we have talked about before by the Mohr-Circle theory, the stress component in the xy coordinate can be related to the stress component in the polar coordinate. Okay, you can just copy down the formula here for the 1.6. Now sigma xx here equal to sigma 0, sigma yy equals 0, sigma xy equals 0. Okay, why? Because sigma yy here have low value, so equals 0, and sigma xy equals 0 too, because there's low distortion, low torsion here. So sigma yy equals 0, sigma xy equals 0. So we end up with a simple description. Okay, and also using the famous formula like this, we can put this term into this form. Okay, and also for the shear stress, we have another formula, and we put sigma yy equals 0 here, sigma xx equals sigma 0, and sigma xy equals 0. This is the stress state along this circular boundary. Okay, by doing this term drops out, this term drops out, we have only these terms. Okay, And we use a very famous formula to turn these two functions into this form. Okay. Now look at here. Sigma RR and sigma R theta is just a combination of periodical function, okay, cosine and sine, and some visually symmetric stress. So according to such kind of situation, we can decompose the boundary condition sigma xx equal to sigma 0 here into two parts, periodical part and the visually symmetric part. Okay, this is what we have done here. Okay, this is the simple tensile stress state, and this is the periodical stress state, and this is the visually symmetric stress state. Okay. Now let us do a summary here. We have a simple tensile stress state here. Okay, this is the original problem we want to deal with, and now we decompose it into problem 1 and problem 2. Problem 2 are having the periodical stress boundary. Okay, boundary stress. And although the problem 2 have the visually symmetric traction boundaries, okay, so we say that the stress function of this problem is phi 1, and the stress function of this problem is phi 2, and then these two stress functions combined together will give you the stress function of this original problem. Okay. So, a summary once again. Original problem, we have such kind of circular plane in simple tensile stress state along the outer boundary B equals R equal B. Inside the plane along the small circular hole R equals small a, and there's loads sigma xx here, traction free is here. Now, this problem can be decomposed into problem 1 and problem 2. Problem 1 with 4 boundary conditions. R equal B, we have sigma RR and sigma R theta. And R equal A, here, R equals small a. R equals small a, you have sigma R equals 0, sigma R theta equals 0. And at R equal B, outer boundary, sigma R equal this, and sigma R theta equal this. For problem 2, we have this boundary conditions. R equal B means that the outer boundary, sigma R equal to sigma 0 over 2, sigma R theta equals 0. And at R equal A, inside the plane, a small hole, sigma R equals 0, low traction here, low normal stress here, and low shear stress here. Okay, and the stress function is phi 1, and the stress function is phi 2, and phi 1 plus phi 2 equal to phi. Okay. Let us continue to solve the problem now. We have already decomposed our original problem into two problems, problem 1 and problem 2. We want to solve these two problems one by one. The first problem, the governing equation is this. This is the biharmonic equation, and this is the circular plane, okay, with a circular hole. Some periodical traction apply on the outer boundary of the circular plate, okay, and inside the small circular hole, it is traction free. We assume that the stress function is a multiplication of Fr and g theta. And this little f and little g is two functions to be determined. Okay, we want to find out what they are. Okay, and you can make a modification here. This is the biharmonic equation for phi 1, bracket 1. Okay, like bracket 1 here. Okay, modify it as bracket 1. We put this function inside this equation. Understand? Okay, let us write down the detail of this operator. This operator is like this. Okay, for simplicity, we define this part of the operator as a triangle. Okay, and this triangle is like this. So this equation become this one and this one. This one is this one and this one is this one. And now note that the triangle operator is the differentiation with respect to R only, without any differentiation with respect to theta. Okay, this is the key point. So this is the differentiation with respect to R. This is the differentiation with respect to theta. Okay, we first apply this. We first apply this to this one and to get this one. So G theta theta, and this one apply to this one to get this one. Okay, this triangle F become this one, and G theta doesn't change. And then G theta theta is just the second order partial derivative of the function G with respect to theta. Okay, and then we carry out the differentiation again. Okay, and this one apply to here to get this one. Okay, and this one apply to here to get this one, and this one apply to here to get this one, and this one apply here to get this one. Okay, now this is a quite complicated equation. Okay, we cannot go further without making some simplification. So we assume that we have this relation. You may ask me, Professor, why you know that you can use this approach to simplify the problem. Okay, I just answered you by saying that such kind of trick, or a little trick, was invented by some previous researcher. So of course there is no systematic approach to be addressed. Okay, so for different special problems, you may have different special tricks. Okay, see here we assume this one. Okay, we assume that this relation hold. Okay, and this is just this, and then we differentiate this identity with respect to theta again to get this one and this one. Differentiate it twice to get this one, differentiate twice to get this one. Now G theta theta equal to lambda G, so we have further simplification. Now G, the function G, the fourth order derivative of function G related to G. So this can be replaced by lambda square G. And this is lambda G, this is G. Okay? In such kind of substitution, we can simplify this equation by taking the function G as the common factor. Okay, this is G and this is lambda G, and this is lambda G is lambda square G, so we can cancel G out, right? So we put this one in this, and this is lambda G, and this lambda G is this lambda square G, and then we cancel G to get this one, right? Now the equation become a little bit more simple now. Especially this equation involves only the independent variable small r. We don't have any theta now, right? We don't have theta here. We have theta and small r here, right? But at this stage now, we have only little r as the independent variable, right? So this is an equation to be solved more easily. Okay, we want to, let me explain it, how to proceed. We want to solve, we assume that phi equal f and g. So we need to find out what is phi bracket 1, right? So we need to find out f and g. Now we already get the governing equation. G, the governing equation here. F, the governing equation is here. So if we can solve this equation to get g, if we can solve this equation to get f, then we get the stress function phi bracket 1, right? If we get the stress function, we can get the stress, and then strain, and then displacement, everything. So this is the key point. So we want to solve this equation to get this, and this solve it to get this, okay? We first try to solve this equation. This equation, in this equation, lambda is a constant. It may be positive, negative, or equal 0. So we assume that we have three kind of situation, and for each kind of cases, for each case, we have different solution. But such kind of mathematical calculations have been done before. We have already talked about this at section 1.4, example 11. So you can consult the example there to help you to understand why we have three cases. And then we want to emphasize that only this solution is useful. This one is not useful. This one is not useful. Why? Because on the boundary r equal b, on the outer boundary, okay, the tractions are periodic function. Okay, they are periodic function. So g theta must be now phi 1 equal to fg. So g theta must be periodic. Otherwise, if this is not periodic, then this is not periodic. Then this stress will not be periodic. So since the boundary conditions are periodic, so we need to see the boundary condition here is sine and cosine. So they are periodic function. So from the stress function, we can compute the stress here. So this is periodic, then this one must be periodic. As a result, we say that we only focus on this part, right? Okay, this is the periodic function, okay? Now, according to the formula of stress function, we can compute the stress component sigma r theta using this formula, okay? And phi bracket 1 is fg. And on the outer surface, we have sigma r theta equal this one, okay? Sigma r theta equal this one, right? Sigma r theta equal this one. This is minus, remember this is minus. This is minus, I think. This is minus, okay? Right. Yes, minus. Yes, I make some mistake, minus, okay? So change it to minus, okay? Minus. So the boundary condition here is like this, and then we have this formula. Now phi bracket 1 is f and little g, the product of f and g. Now we perform the differentiation here to f, and the differentiation here to g, right? This is the differentiation with respect to theta operating on g. This is the differentiation of r operating on f. So we get this one and this one, okay? Of course, r equal to little b. Now we put this formula, means that this formula into here, and then carry out the differentiation to get this one. See, differentiate cosine become minus psi, right? And then 1 square root minus lambda comes out. And then differentiation this term become cosine, right? And then 1 minus lambda square root comes out. Okay? So now we compare the right hand side and the left hand side, right? The left hand side we have sine 2 theta. So at the right hand side we have sine 2 theta here. So minus lambda square root equal to 2, okay? In order that this one becomes sine 2 theta, right? Understand? And also, we don't have any cosine term here. We don't have cosine term here. So A2 becomes 0 here, okay? Understand? So A2 becomes 0, and then minus lambda square root becomes 2. Okay, we write it like here to understand that lambda equal to minus 4, okay? So in this way, we had already obtained the solution of G because A2 equals 0. A2 equals 0, so this drops out. And then this one equals 2. So okay, we have this one, right? So finally, we have obtained the function G theta. And also, lambda equal to minus 4. Another job is to compute F. Lambda equal to minus 4. So we put this value into 4.3.2 to get this equation. Understand? Let me show you. This one, lambda equal to minus 4. Lambda equal to minus 4. Lambda square equal to 16. That's it. So we get this equation. Now the triangle operator is like this. I remind you once again. And this is a what? A Euler equation. And we have already solved this equation before in section 1.4, right? So I just go through the calculation quickly. We assume that little f equal to Ra, and then we get A equal to 2, 4, minus 2, 0. In example line of 1.4, you have already computed this one. So we say that f R equal to Ra, so A equal to 2, 4, minus 2, so this A equal to 2, so R square, this one. A equal to 4, so R4, right, this one. A equal to minus 2, R minus 2, this one. And A equals 0, so R0 is equal to 1, so this is a constant term, okay? So we have the general solution of little f like this. You can consult the example line in section 1.4. Okay, up to now we had already obtained the function f and g, right? So we write the stress function phi bracket 1 equal to fg, and this is f and this is g. And now we take this a1 into here. Your a1 times a star equal to big A. Okay, a1 times b star equal to big B. A1 times C star equal to big C. A1 times D star equal to big D, right? So we have such kind of things. So in this way, A1 disappears. Now we have this formula for the stress function. We can use the following formulas to calculate the stress component: sigma RR, sigma theta, theta, sigma R theta for problem 1. Okay, so put this into here, this into here, and this into here, and then we get this one and this one, this one. Now we have already obtained the stress component, but there are some unknown constant A, B, C, D, right? A, B, C, D inside the stress function, inside the stress components. How can we determine this unknown constant? We use the boundary condition to help us to determine this A, B, C, D. How many constants to be determined? 4. 4 unknown constants. So need to be determined. So we need 4 conditions, right? So we consider 4 boundary conditions here. This is one boundary condition, another one boundary condition, and also inside small r equal to small a, sigma r equals 0, then sigma r theta, the shear stress, also equals 0. Understand? So we have 4 conditions. 1 condition, 2 condition, 3 condition, sigma r equals 0. 4th condition, sigma r theta equals 0. Understand? So in the outer boundary, the normal stress and shear stress equals 0. 2 conditions. Along the inner boundary, the normal stress and the shear stress equal to 0. Another 2 conditions. So totally we have 4 conditions. Okay? Normal stress, shear stress, normal stress, shear stress. In inner boundary, outer boundary, right? Outer boundary and inner boundary, 0, 0. And then this is the periodic function we have. We just put the little r equal to b here because in the outer boundary little r equal b, right? Like this, sigma r. Here we have r. So r4 replaced by b4. R square replaced by b square. R fourth power replaced by b fourth power. Is b square, something like this. So we have such kind of conditions, okay? Not this one, this one. Make some mistake, replaced, okay? So no matter how, the normal stress and shear stress become like this at the outer boundary. So see here, we have little r now. We have little b, little b, little b, little b, okay? We have 2 conditions. Another two conditions. This is the normal stress, okay? Now little b become little a in the inner boundary, right? Inside the circular plane, inner boundary. Okay, and then b replaced by little a, b a, b a, right? So we have 4 equations for 4 unknowns. Okay, so we just solve this directly, and this directly, this directly. Okay, finally, we say that we take b in to infinity. Okay, b take to infinity. Okay. To get this one, this one, this one, become this one, this one, this one become, let me see, yes, this one become A, yes, and why B equals 0, let me see, and this one, from here and here. Okay, we can solve this one. Okay, here, remember, such kind of limit is not very appropriate. Why we take such kind of limit? Because we are considering a problem like this, okay? Now we add in a practical condition that the hole here is very, very small. Okay, like in a steel member, we have a little small bore hole. Okay, so the radius here B is very big, and the radius here A is very small. Okay, so the appropriate condition is B much bigger than little a. Okay, this is the correct limit we should take. Okay, so please change this condition to B bigger and bigger than a. B larger and larger than small a. Okay, with such kind of limit, okay, you can turn these 4 conditions into these 4 conditions. Okay, don't take this. This doesn't work. Okay, also please make a modification here. Okay, once we have these 4 conditions, we put this. Once we have these 4 constants, we put these 4 constants into the formula before. This one. To get the stress component like this. Okay. Here in this formula, we don't have little b anymore because by taking the limit b much bigger than a, then the value of b will be cancelled. This is very important because we are dealing with a problem using the free body diagram, right? So you should ask me, what is the size of little b here? See, we want to deal with this problem. We cut a free body here. The outer radius is b, little b, right? But how large is b? Okay, there's no definite answer. But see, as we have done, by taking the limit that how big is b? B is much larger than a, then you are okay. Understand? So we don't care about the precise value of b. So long as b is much larger than a, then we can apply the solution we had obtained. Okay? So the value of little b shouldn't appear in the final result because there is no definite answer for this size, for the size of this free body. So, as a result, we have the stress component only expressed in terms of the radius of the little hole, which is equal to little a. Okay. Now we have already solved the first problem. We turn to the second problem. By solving the second problem, we let our stress function as Fr without any function depend on theta. Okay, why? Because it is a symmetric problem. Okay, let me show you. Problem 2. Yes, problem 2 here. Problem 2, it is a circular plate with a circular hole subjected to what? To some radially symmetric loading. So you can expect that the stress distribution doesn't depend on the value of the angle theta, right? So we have a radial symmetry here. In this way, we have only also 4 conditions. Okay, 1, 2, 3, 4. Okay, and then outer boundary and inner boundary, outer boundary, inner boundary. Okay, so we can assume that this stress function depends only on small r. It doesn't depend on theta, right? Okay. So we assume that phi 2, the second problem, is, the stress function of second problem equal to Fr. Okay. By doing this, we substitute this formula into here to get this one. Okay, and this is the Laplacian. And now, since Fr will be eliminated when it is subjected to the partial differentiation with respect to theta. So when we carry out the differentiation here, then it is equal 0. Okay, so it doesn't matter that we have such kind of operator. It doesn't give us any practical result. So we have only focus on here and here to get this one. Okay, and now this one replaced by this one replaced by this one. This is a Euler equation again. Okay, we have already solved this equation before in section 1.4, example A. So we just repeat the result quickly. Fr equal to Ra, so put it here. Okay, right? And this is the operator, this is the operator. Okay, and then we operate this operator to this function to get this one. And then operate this operator into here to get this one, okay? So finally, we do some reorganization to get this one and end up with A equals 0 and A equals 2, okay? Double roots. For such kind of cases, double roots, we have the general solution for the little f like this, okay? Such kind of general solution have been obtained before in section 1.4, example A. And then we put this stress function into here, here and here to get the formula for the stress component, okay? And now we have three conditions, B, C, D, B, C, D. We don't have A anymore, how many conditions we have? We have 4 conditions, okay? But 2 of them is not needed because the shear stress here equals 0. Understand? The shear stress here equals 0. So shear stress equals 0 here in the outer boundary and inner boundary. These 2 conditions are satisfied automatically because inside the body we have already loaded the shear stress equals 0. Okay, so of course at the boundaries, outer and inner boundaries, the shear stress equals 0. So we have only 2 conditions. Yes, here. We had already loaded inside the plate, the shear stress equals 0. So the boundary condition for the using the shear stress are satisfied automatically. So we have only 2 boundary conditions for this problem. Which 2? These 2, not written by the shear stress, but written by the normal stress. Normal stress equals to sigma 0 over 2 here at R equal B. At R equal A, normal stress equals 0 here. Understand? Understand we have 2 conditions written by normal stress, expressed by normal stress at the outer and inner boundary. 2 conditions only. But we have 3 constants to be determined. Okay, here we have 3 constants, B, C, D, right? B, C, D, yeah, B, C, D, right? C, D, B, C, D. So we have 3 conditions, 3 constants, but we have only 2 conditions. So we don't have enough of conditions to determine the constant now. But don't worry, we apply one more extra constant, condition. We say that if D not equals 0, then it can be shown that later the displacement field computed from the stress field will be unreasonable. Okay, we will do such kind of reasoning later. Okay, so in this way, we understand that D must equal 0, okay, in order to have reasonable result for the displacement. By arguing this, then the stress field now written as this one and this one, this one. We don't have D anymore, right? We don't have big D anymore. We have BC, BC. So we have only two conditions, two constants will be solved by two conditions. Understand? Let us do some review. Here, B, C, D, D equals 0, 0, 0 drops out, 0, 0, 0 drops out. We have taken this part and this part, okay? So we have this one, and this one. Now, at the outer boundary, R equal to little b, we have the normal stress equal to sigma c over 2. And then this R equal b. In the inner boundary, R equal a, right? And the normal stress equals 0. So we have two conditions, two equations for two unknown b and c. Solve it. Solve it here. So, and also, at this stage, we apply the conditions that b is much bigger than a. With this condition, we have sigma 0 over 4. How? If b much bigger than a, then this term can be replaced by b squared only. Is b much larger than a squared, right? So this term can be negated. We have only this term, so this term and this term drops out to get this one. Understand? At the same way, here, this term can be replaced by minus b squared only. So this term drops out, okay, to get this term, okay? So we have BC to take it back here, okay, to get this one equal to this one equal to this one. So finally, we get the stress field for the second problem. So we sum up the stress field for the two problems, okay? The stress field for the first problem, the stress field for the second problem, to get the stress field for the original problem. Understand? So here, the stresses in the plate with a hole, a small hole, outside the free body here, the stress is already known. It is in the simple tensile stress, okay? According to the what Singularity principle, outside this circular region here, here, okay, and here, the stress state is in simple tensile stress state, and inside the circular region close to the little small hole, we have the stress like this, okay, which is the combination of two problems, okay, like this. And as a result, we have already find out the stress field for the whole plate.